Moon collision with Earth. Total destruction explained. Hello everyone. Today we are going to explore a scenario we're talking about the Moon colliding with Earth and the total destruction that would follow. From massive tidal waves to earthquakes, volcanic eruptions, and a planet-altering impact, we'll break down exactly what could happen step by step. Buckle up, because this is going to be intense. Billions of years ago, a version of our Earth that looks very different than the one we live on today was hit by an object about the size of Mars called Day. And out of that collision, the Moon was formed. How exactly that formation occurred is a scientific puzzle researchers have studied for decades, without a conclusive answer. Our solar system began to take shape about 4.56 billion years ago. As the Sun's core ignited nuclear fusion and the protoplanetary disks surrounding it then began to fragment and form tiny protoplanets. After about 50 million years had elapsed, many of the worlds, including planets and moons that we are familiar with, had already taken shape. However, a fateful collision between Earth and a large, subsumed protoplanet named They kicked up an enormous cloud of debris that surrounded our home planet in a torus-shaped structure known as a synestia. Some of that material escaped into interplanetary space. Some fell back onto Earth, but the remainder coalesced and formed the largest natural satellite ever found around a rocky world, our own Moon. For the past 4.5 billion years, the Moon has affected Earth in many ways. It's the major cause of tides on our planet and also helps stabilize our axial tilt over time. It's the primary cause of why the duration of a day on Earth lengthens over time. And it's the cause of all total solar, annular solar, and lunar eclipses that our world has ever. Most theories claim the Moon formed out of the debris of this collision, coalescing in orbit over months or years. A new simulation puts forth a different theory. The Moon may have formed immediately. In a matter of hours, when material from the Earth and Theia was launched directly into orbit after the impact. This opens up a whole new range of possible starting places for the Moon's evolution, said Jacob Kagors, a postdoctoral researcher at NASA's Ames Research Center in California's Silicon Valley, and lead author of the paper on these results published in the Astrophysical journal Letters. We went into this project not knowing exactly what the outcomes of these high-resolution simulations would be. So, on top of the big eye-opener that standard resolutions can give you misleading answers, it was extra exciting that the new results could include a tantalizingly moon-like satellite in orbit. The simulations used in this research are some of the most detailed of their kind, operating at the highest resolution of any simulation run to study the Moon's origins or other giant impacts. This extra computational power showed that lower resolution simulations can miss out on important aspects of these kinds of collisions, allowing researchers to see new behaviors emerge in a way previous studies just couldn't see. A puzzle of planetary history understanding the Moon. This origins requires using what we know about the Moon, our knowledge of its mass, orbit, and the precise analysis of lunar rock samples, and coming up with scenarios that could lead to what we see today. Previously prevailing theories could explain some aspects of the Moon's properties quite well, such as its mass and orbit, but with some major caveats. One outstanding mystery has been why the composition of the Moon is so similar to Earth's. Scientists can study the composition of a material based on its isotopic signature, a chemical clue to how and where an object was created. The lunar samples scientists have been able to study in labs show very similar isotopic signatures to rocks from Earth. Unlike rocks from Mars or elsewhere in the solar system, this makes it likely that much of the material that makes up the Moon originally came from Earth. In previous scenarios where they sprayed out into orbit and mixed with only a little material from Earth, it's less likely we'd see such strong similarities, lest they was also isotopically similar to Earth, an unlikely coincidence. In this theory, more Earth material is used to create the Moon, particularly its outer layers, which could help to explain this similarity in composition. There have been other theories proposed to explain these similarities in composition, such as the synestia model where the Moon is formed inside a swirl of vaporized rock from the collision. But these arguably struggle to explain the Moon's current orbit. This faster, single-stage formation theory offers a cleaner and more elegant explanation for both these outstanding issues. It could also give new ways to find answers for other unsolved mysteries, This scenario can put the moon into a wide orbit with an interior that isn't fully molten, potentially explaining properties like the moon's tilted orbit and thin crust, making it one of the most enticing explanations for the moon's origins yet. Getting closer to confirming which of these theories is correct will require analysis of future lunar samples brought back to Earth for study from NASA's future Artemis missions. The scientists gain access to samples from other parts of the moon and from deeper beneath the moon's surface. They will be able to compare how real-world data matches up to these simulated scenarios and what they indicate about how the moon has evolved over its billions of years of history, a shared origin beyond simply learning more about the moon. These studies can bring us closer to understanding how our own Earth became the life-harboring world it is today. The more we learn about how the moon came to be, the more we discover about the evolution of our own Earth, said Vincent Eek, a researcher at Durham University and a co-author on the paper. Their histories are intertwined and could be echoed in the stories of other planets changed by similar or very different collisions. The cosmos is filled with collisions. Impacts are an essential part of how planetary bodies form and evolve. On Earth, we know that the impact with Theia and other changes throughout its history are part of how it was able to gather the materials necessary for life. The better scientists can simulate and analyze what's at play in these collisions, the more prepared we are to understand how a planet could evolve to be habitable like our own Earth.